Sometimes we write programs in which we would like to know the time and date. This information is easy to get. To find out the current time, there are three system calls. Second, which takes no arguments, returns an integer from 0 to 59. Minute, also with no arguments, returns an integer from 0 to 59. And hour, which also takes no arguments, is on the 24-hour clock. So we get back a number from 0 to 23. Here, 0 is midnight, 12 is noon, and 23 is 11 o'clock at night. With this information, we can draw a clock. Here's a very simple clock. The time right now is about 10:42. You can see that the hour and minute hands are drawn in gray, and the big red second hand is sweeping its way around. It's very easy to draw this clock. I just translate to the center of the circle, and then I rotate to draw each of the three triangles. Normally, each triangle is pointed straight upwards, but I rotate it using the value of seconds, minutes, or hours to put it in the right position. Now watch the minute hand as we come up on the top of the minute. Chunk. The minute hand jumped because the value we get back from minute is an integer, and we just went from 42 to 43. There are clocks in the real world that behave this way, but a lot of clocks move much more smoothly. The minute hand smoothly makes its way from 42 to 43 over the course of a minute, and the hour hand also smoothly moves from 1 hour to the next. So right now, when we're almost 3/4 of the way from 10 to 11 o'clock, we would expect the hour hand to be about 3/4 of the way, instead of pointing exactly at 10. Can we do this? Of course we can, and it's easy. The problem is that second, minute, and hour are returning integers, and we really want to be using a float. So let's create a new float to hold the value of minutes. It'll be the integer we get back from minute plus a floating point value from 0 to 1, and that will just be s over 60. So as the second hand works its way from 1 minute to the next, the value of minute will gradually go up from 1 minute to the next. We can do the very same thing for the hour. I'll create a float called f_hour, and I'll add the floating point minutes that we just computed, divided by 60, to the hour. So as the minutes go from 0 to 60, the hour will smoothly blend from one integer to the next. I used f_minute here rather than just m because I wanted to use the extra little floating point value that we found when we added s over 60 to m. It's a very subtle difference, but this is the way real clocks do work, so why not do it right? Let's return to our clock and see what this change looks like. It's about 10:46 right now, and notice that the hour hand is indeed a little bit more than 3/4 of the way from 10 to 11. Now we're about to hit the top of the minute, so watch the minute hand. And that's beautiful. The hour and minute hands are moving nice and smoothly. Of course, there's no reason why we have to draw clocks that look like traditional clocks at all. Here's another kind of clock. There are a bunch of discs and a vertical line, and we read the time by reading the numbers under the vertical line, starting with the innermost disc. So the inside disc represents hours. Nighttime hours have a dark gray background. Right now, the vertical line is just a shade before the 11. So it's not quite 11 yet, it's 10 something. So we look at the next ring out, and we see that we're just past the 10. So it's 10:52 and something. Then we look at the outermost ring, and that's the seconds. And now you can see that we're working our way up. We're at just about 55 seconds, and as soon as we reach the 12, we'll go to the new minute. There we go. So we don't have hands in this clock. Instead of a static dial with 3 hands that move, we have a static hand, which is the vertical line, and 3 dials that move. The outermost ring I use to show the color of the sun. So when it's dawn, that ring starts to move into the yellows. At noon, it becomes bright yellow. As the afternoon comes in, it goes into sort of an orange dusk color. At night, it turns dark. And that's just a little extra enhancement because I thought it would look pretty. Here's an abstract kind of a clock. We start with a regular grid of dots, nicely organized into smoothly changing colors. There's one dot for every second. Right now, we're near the start of the hour, and at the start of each new second, another dot breaks free of the grid and falls down the screen on a nice curved path, where it ends up in some unpredictable location. The idea here is that at the start of an hour, we may be very organized and we have a clear idea for everything we're going to accomplish. But by the end of the hour, we can look back and see that life surprised us, and the seconds and minutes went by not as we planned, but as reality unfolded. This clock doesn't tell us what hour it is. It assumes you know that. It doesn't even give you numerical values for the minutes or seconds. Instead, it's designed to give you a feeling for how far into the hour we are. Jumping ahead, here we are at a quarter after the hour, when the red and most of the yellow dots have fallen. Zipping ahead again, now we're at 45 minutes into the hour. And near the end of the hour, only a few purple dots remain to fall. Just for fun, I can make all the dots fall at once. This way, we can see what happens over the course of the hour. If I don't redraw the background on every frame, we can clearly see the curved path taken by each dot. In fact, these are all just single Bezier curves. Abstract clocks are great fun to design and program because you can do things on the computer that you just can't build mechanically. Let's now turn our attention from the current time to the current date. You won't be surprised to learn that we have 3 function calls to find out the current day. Day, which takes no arguments, gives us back an integer from 1 to 31, telling us where we are in the current month. Month, also no arguments, gives us back an integer from 1 to 12, telling us whether the month is January, February, and so on. Finally, year, which takes no arguments, returns an integer, giving us the current year. With this, of course, you can create calendars and date books and anything else that relies on the date. There's one more thing that's really useful to know, and that's how long your program has been running. There's a function called millis. It returns an integer, and it tells you how many milliseconds, or thousandths of a second, have elapsed since the time your program started. So let's see this visually. Suppose that each of these pink boxes represents a frame. So we'll number them. This is the start of each new frame. And at 60 frames per second, it works out that we get about 17 milliseconds per frame. So if I am getting 60 frames per second, if I execute this line at the top, m equals millis with no arguments, at the start of draw, I'll get back the numbers in the top row. That's how many milliseconds have elapsed since the program began. And if we squish this together and look forward out to the 60th frame, by the time we hit frame 60, we will have been running for just about 1,000 milliseconds. It's really very rare that you care how long a program has been running. Usually, you use millis to compute a time difference. When something begins, you call millis, and you save that number. Then later, you can call millis again. If you subtract the value you saved, then you know how many milliseconds, or thousandths of a second, have elapsed since the start of the event when you saved the starting time. Using millis in this way really depends on exactly what it is you want to do, and it's not something you'll do very often. But when you want to know very precisely how long it's been between two events, millis is a really good way to find out. To wrap things up, here's a combination of a clock and a calendar. The line, reading from left to right, represents an entire year, and the little circles represent the beginning and ends of every month. The bright yellow circle is today, and right now it's near the end of November, and so we're near the end of the 11th segment in the line. I imagine that this would be hanging on a wall somewhere, like a calendar, so to make it a little bit interesting, it changes very, very slowly over time. Here I'll speed things up by a huge amount, and we can see the motion that gets applied. The little circle represents not just the day, but also the time, so it moves incredibly slowly over the line, but nice and smoothly. I'm sure you can think of lots of variations on this calendar clock, and coming up with new designs for clocks and calendars is a lot of fun.